In October of 2017, a robotic telescope in Hawaii, built to hunt for asteroids that might one day threaten Earth, caught a faint point of light doing something no object had ever done before. It was moving too fast to be bound by the sun's gravity. It had come from nowhere within our solar system, and it was leaving just as quickly, on a path that would carry it back out into the depths of interstellar space, never to return. Astronomers gave it a name that captures exactly what it was: Oumuamua, a Hawaiian word that roughly translates to a messenger from afar arriving first. It remains, to this day, one of the strangest objects ever observed by human beings, and even now, years after it vanished into the dark beyond Neptune, scientists are still arguing about what exactly it actually was. To understand why Oumuamua caused such an uproar, you have to understand what astronomers were expecting to find, eventually, from beyond our solar system. For decades, scientists had predicted that our solar system must occasionally be visited by objects from other star systems. Every planetary system, as it forms, flings debris outward the way a spinning garden sprinkler flings water droplets. Planets and dwarf planets shove smaller rocks and icy bodies around with their gravity, and some of that debris gets kicked out entirely, launched into the emptiness between the stars, drifting for millions or even billions of years. Multiply that process by the roughly 100 billion star systems in our galaxy alone, and you get an environment thick on a galactic timescale with wandering fragments of other worlds. The math suggested that some of this drifting material must occasionally wander close enough to our sun to be noticed. It was just a matter of having a telescope sharp enough and patient enough to catch one in the act. That telescope turned out to be Pan-STARRS, a survey instrument perched atop the Haleakala volcano on Maui, whose entire job is to scan the sky night after night looking for anything that moves against the fixed background of stars. On October 19, 2017, it found a dot of light that was moving in a way its software had never modeled before. Follow-up observations over the following days confirmed the impossible. This object's path curved around the sun, not in a closed ellipse like every planet, asteroid, and comet in the solar system, but in a hyperbola, an open curve that meant it was never gravitationally bound to our sun in the first place. It had swept in from outside, made its closest pass, and was now on its way out, permanently. Its velocity relative to the sun, once you subtracted out the sun's gravitational pull, was roughly 26 kilometers per second, a speed inherited from wherever and whenever it began its journey. Astronomers traced its incoming path back toward the direction of the constellation Lyra, though pinning down an exact parent star has proven essentially impossible because over the likely hundreds of millions of years, or longer, that Oumuamua spent drifting through the galaxy, the stars themselves have shifted position and the object's trail has been erased by time. What made Oumuamua truly bizarre wasn't just where it came from. It was what it did while it was here. As telescopes around the world scrambled to observe it before it faded from view, the brightness of the object began to flicker dramatically, changing by a factor of 10 as it tumbled through space. That kind of extreme variation in brightness, repeating on a period of roughly 7 to 8 hours, told astronomers something remarkable. This thing was not shaped like a typical asteroid or comet. Most small bodies in our solar system are roughly potato-shaped, or at most twice as long as they are wide. To produce the kind of light curve Oumuamua displayed, astronomers calculated it had to be extraordinarily elongated, perhaps 5, 6, or even 10 times longer than it was wide. Picture something shaped less like a boulder and more like a cigar, or a surfboard, or a discarded pen tumbling end over end through the dark. No natural object we had ever seen up close, not in our own solar system's asteroid belt, not among any comet ever imaged by a spacecraft, looked anything like this. And then there was the color, and the way it reflected sunlight. Oumuamua appeared reddish, similar in tone to many objects out in the distant icy reaches of the solar system, the kind of dull, rusty hue you get when organic compounds have spent eons being irradiated by cosmic rays, forming a kind of crust. That at least fit with an object that had spent a very long time drifting through the radiation-soaked vacuum between stars. But here's where things got genuinely strange. Oumuamua showed absolutely no visible coma or tail. When a comet from our own solar system swings close to the sun, the heat vaporizes ices on its surface, releasing gas and dust that form the glowing halo and streaming tail we associate with comets. Oumuamua showed none of that, even though its icy reddish surface and its trajectory looked in many respects cometary. It behaved, in other words, like an asteroid, a bare rock with no active outgassing. Astronomers initially classified it as such, except it wasn't behaving quite like an asteroid either. When researchers carefully tracked Oumuamua's position over the weeks after discovery, they noticed its trajectory wasn't quite matching what gravity alone predicted. The object was accelerating very slightly as it moved away from the sun, more than gravity could explain on its own. For comets, this kind of extra non-gravitational nudge is completely normal and well understood. It's caused by the rocket, like thrust of gas jetting off in sunlit, vaporizing surface. But Oumuamua showed no visible sign of that gas or dust. It was as if something was gently pushing it, invisibly, without any of the usual fireworks. This one detail, a barely perceptible extra shove with no obvious cause, became the single most debated feature of the entire object. And it's the thread that nearly every scientific explanation for Oumuamua has had to somehow account for. Naturally, the mystery invited some extraordinary speculation. Because the puzzle involved an unusual shape, an unexplained acceleration, and an object behaving unlike anything catalogued before, a small number of scientists, most prominently the Harvard astronomer Avi Loeb, raised the possibility that Oumuamua might not be a natural object at all. Loeb proposed that the strange acceleration could be explained if Oumuamua were extremely thin and flat, functioning almost like a solar sail, something that could be pushed gently by the pressure of sunlight itself, the way a sheet of paper is nudged by a fan. He suggested this might indicate artificial origin, a probe or fragment of a probe sent by an alien civilization. It's important to say plainly that this idea captured enormous public attention, and it is also the interpretation least supported by the broader scientific community. A large international team of over a dozen astronomers, chemists, and planetary scientists formed specifically to review every piece of evidence about Oumuamua, published a comprehensive assessment concluding that every one of its properties, its shape, its color, its lack of visible tail, its subtle acceleration, could be explained by natural processes, and that no feature required an artificial explanation. That doesn't mean the idea was dismissed for being provocative rather than examined. It means that when scientists tested the artificial object hypothesis against the data, simpler natural explanations kept fitting just as well or better without requiring us to assume the existence of alien engineering. So what are those natural explanations? Over the years, since 2017, several serious hypotheses have been proposed, refined, argued over, and in some cases discarded, in a process that is a genuinely wonderful example of the scientific method working out in the open. One of the earliest and most influential ideas came from Daryl Seligman and Gregory Laughlin, who suggested that Oumuamua might be made largely of frozen hydrogen, a substance so cold and so volatile that it could sublimate, turning directly from ice into gas, quietly and invisibly, without producing the bright, dusty tail typical of water ice comets. This hydrogen ice, outgassing could, in principle, supply exactly the gentle extra push that was observed, while releasing so little visible material that no coma would ever form. It was an elegant idea, and it briefly became one of the leading contenders, but subsequent research revealed a problem. Solid hydrogen ice is thought to sublimate away almost immediately when exposed to the ambient warmth of interstellar space and to cosmic ray bombardment. An object made of it likely wouldn't survive the journey of hundreds of millions of years needed to reach us in the first place. The idea remains debated, but it faces serious physical hurdles. A second, and arguably more influential, idea came from Stephen Desch and Alan Jackson at Arizona State University. They proposed that Oumuamua might be a fragment of nitrogen ice, the same material that coats large portions of Pluto's surface and the surface of Neptune's moon, Triton, both of which were revealed in stunning detail by NASA's New Horizons mission. Desch and Jackson ran calculations working backward from Oumuamua's exact size, its shininess or albedo, the way it tumbled, and the precise strength of its mysterious extra acceleration, and asked what material, sublimating under sunlight, would produce exactly this behavior. The answer that fit best, remarkably, was nitrogen ice. Not only did the physics line up, but the reflectivity required for the math to work matched almost exactly the reflectivity we already measure on the surface of Pluto and Triton. Their proposal went further. They suggested Oumuamua might be a shard, blasted off the surface of an entire Pluto-like world, an exo-Pluto, orbiting a distant star during some ancient collision billions of years ago. As that shard tumbled through the void for eons, it would have slowly lost its outer layers to sublimation, growing thinner and more elongated over time, the way, as the researchers memorably described it, a bar of soap grows thinner and more oddly shaped the more it's used. If that story is right, Oumuamua wasn't really a comet or an asteroid, but something else entirely. A chip off the icy crust of an alien world we will never see up close, wandering the galaxy for what could be hundreds of millions of years before, drifting, by pure chance, into our solar system's field of view for a matter of weeks. That nitrogen iceberg theory hasn't gone unchallenged. Other researchers, including Amir Siraj and Avi Loeb, pointed out a significant problem. to produce enough nitrogen ice fragments scattered throughout the galaxy for us to have plausibly detected one by pure chance, you would need an enormous, almost implausible amount of the galaxy's nitrogen locked up in Pluto-like bodies, more than current models of planet formation seem to allow. Other teams reached similar conclusions, suggesting that the population statistics simply don't add up, and that if Oumuamua really were a fragment of an exopluto, we should be either finding far more of these objects, or the mechanism generating them would need to be far more efficient than seems physically reasonable. It's a genuinely unresolved argument playing out across competing scientific papers, which is exactly the kind of healthy disagreement good science runs on. Then, in September of 2025, a new piece of indirect evidence arrived from an entirely unexpected direction, and it's some of the most exciting recent context for this whole mystery. Using the Hubble Space Telescope, a team of astronomers studied a white dwarf star, the dense, burnt-out core left behind after a sun-like star dies, located about 145 light-years away. White dwarfs are cosmic forensic tools. As their gravity slowly shreds and devours any leftover asteroids, comets, or planetary fragments orbiting them, the star's atmosphere becomes polluted with the chemical signature of whatever it just consumed. In this case, astronomers detected an unusually high concentration of nitrogen, alongside carbon, oxygen, and sulfur, being accreted onto the white dwarf, a chemical fingerprint strikingly similar to the composition we see in Kuiper Belt objects out beyond Neptune, the same population of icy bodies that includes Pluto itself. It was, in essence, direct evidence that nitrogen-rich, Pluto-like debris fields genuinely do exist around other stars, and that such material really does get scattered and, eventually, in some cases, presumably ejected into interstellar space. It doesn't prove Oumuamua itself was a nitrogen iceberg, but it does something almost as valuable. It shows that the raw ingredient at the center of the theory, nitrogen ice from exo-Pluto-like worlds, is a real confirmed thing floating around other solar systems, not just a convenient hypothesis invented to explain one weird visitor. More recent modeling, from a 2025 study published in monthly notices of the Royal Astronomical Society, has also explored yet another mechanism, tidal fragmentation. This idea proposes that Oumuamua's extreme elongated shape might have been carved not by slow sublimation, but by a violent one-time event, a close gravitational encounter with a star or even a white dwarf, during which powerful tidal forces stretched and tore apart a larger parent body, flinging fragments outward, including one long, thin, taffy-like shard that would go on to become Oumuamua. Researchers ran long-term simulations of planetary systems to see whether this kind of close stellar encounter, combined with the presence of a giant planet nudging objects into just the right orbits, could plausibly produce Oumuamua-shaped debris, and found it to be a workable, physically reasonable pathway. It's yet another candidate explanation sitting alongside the nitrogen iceberg and hydrogen ice hypotheses, each with its own strengths, its own critics, and its own open questions. It's worth pausing here to appreciate just how remarkable it is that we're even having this conversation, arguing over multiple detailed, physically grounded models for a rock we glimpsed for barely a few weeks, 3 million miles away, before it vanished. Oumuamua was never photographed up close. No spacecraft got anywhere near it. Every single thing we know, its shape, its spin, its color, its chemistry, its subtle, unexplained acceleration, was reconstructed purely from the faint flickering of reflected sunlight, gathered by telescopes here on Earth, over a window of time so short that by the time most of the world had heard the news, the object was already too faint to study further. It's a bit like trying to determine the exact species, diet, and behavior of an animal from a single blurry photograph taken through a car window as it disappeared around a corner. That we've managed to narrow the possibilities down this far and build genuinely testable competing theories is a testament to how powerful modern astrophysics has become, even when working with almost nothing. Oumuamua is gone now, permanently, having swept within about a quarter of the distance from the Earth to the Sun during its closest approach in September 2017. It has been steadily receding ever since, crossing the orbit of Mars, then Jupiter, then Saturn, and is now well beyond the reach of any telescope currently in operation, heading out toward the constellation Pegasus, never to return to our solar system again. Researchers have seriously studied whether a spacecraft could have been launched to chase it down. Project Lyra, a collaboration between engineers and astronomers, worked through the punishing orbital mechanics required to catch an object moving that fast, and concluded that while a mission would have been extraordinarily difficult, requiring either a very early launch or an audacious maneuver that dives close to the Sun to use its gravity as a slingshot, it was not, in principle, physically impossible. No such mission was ever launched. Oumuamua slipped away, carrying its secrets with it, and unless another object exactly like it wanders through the solar system again, we may never fully resolve the debate over what it really was. But here's the remarkable twist. Oumuamua was not alone for long. In 2019, just 2 years later, astronomers spotted a second interstellar visitor, Comet 2I Borisov, which behaved in a far more familiar way, actively venting gas and dust in a classic, unmistakable cometary tale, confirming that interstellar comets do indeed pass through our solar system and behave the way physics predicts. Then, in July of 2025, a third interstellar object arrived. 3I Atlas, another comet, observed actively releasing water vapor as it approached the Sun, giving scientists their best look yet at the chemistry of material from another star system. With 3 interstellar visitors now confirmed in less than a decade, and new survey telescopes like the Vera C. Rubin Observatory expected to discover many more such objects as it comes into full operation, astronomers increasingly suspect that Oumuamua wasn't some singular anomaly, but rather the first known member of an entire previously invisible population, wanderers between the stars, of which some may be icy comets, some rocky fragments, and perhaps, if the exopluto theory holds up, occasional shards of nitrogen ice cast off from worlds we will never see directly. Each new interstellar object we detect adds one more data point, one more chance to compare, contrast, and eventually understand just how unusual or how ordinary Oumuamua truly was. Step back far enough, and the whole story becomes almost dizzying to contemplate. Every planet, moon, and icy world orbiting every star in the galaxy is, over sufficiently long timescales, shedding material outward into the space between stars, an endless, silent snowfall of rock and ice drifting through the galaxy on timescales of hundreds of millions or even billions of years, largely invisible to us, simply because interstellar space is so achingly vast and so profoundly dark that even a mountain-sized chunk of another world reflects essentially no light at all until it happens to wander, by pure chance, close enough to a star for us to catch a fleeting glimpse. Oumuamua was one such glimpse, a brief flash of visibility in an ocean of permanent darkness, a genuine emissary, whatever its exact origin, from a solar system we will likely never identify, carrying within its structure, whether ice or rock, ancient nitrogen or ancient hydrogen, a physical record of processes that unfolded around another star, long before it ever crossed paths with our own. We still don't know with total certainty exactly what Oumuamua was. It might be a fractured piece of an alien Pluto, worn thin over eons like a bar of soap dissolving under running water. It might be a rare, fragile iceberg of frozen hydrogen that somehow survived long enough to reach us. It might be the torn-off remnant of some larger world, or ripped apart by the tidal grip of a star it once passed too close to. What we do know is that it was real, that it was genuinely unlike anything ever observed before or since, and that for a few short weeks in the autumn of 2017, humanity looked up and, for the very first time in recorded history, watched a fragment of another solar system tumble silently past our own before disappearing back into the dark. It came from a messenger that arrived without warning, delivered no clear message, and left us with a question that we are, even now, still working to answer.